Welcome to the lecture on kernel memory allocation. So in this lecture, we'll study about two kinds of allocators in the Linux kernel, which are the buddy allocators and the slab allocator. So basically, there are different versions of the slab allocators. So they are actually called slob, slab, and slub, right? So in general, the name of the allocator is in all caps. I should have had this in all caps. So this basically has three different versions. So we will discuss what these are, but we'll first start with buddy and then we'll move on to slab. They are for different purposes. So the buddy allocator is more for generic kernel allocation, and the slab allocator is for specific objects, right? It's for initialized objects. So their purpose is different, and we will come to them in due course of time. So in buddy allocation, the main idea is that let's say we are given physical memory, a large chunk of physical memory, and we need to manage it. So manage means what? Manage means basically allocate and deallocate. So requests will come, they will say that look, I want to increase my virtual memory footprint by let's say 4 pages or 5 pages or 6 pages, so where a page is the least count. And how would they come? They would come via the BRK system call, which would basically say that look, I'm not happy with the amount of virtual memory that I have, so I need more space. And so the moment that we have requests of such kind, there will be a need to allocate space. So what the buddy allocation can do is that it can provide large chunks of arbitrary physical memory sizes, physical memory chunks to processes. So we have already discussed the idea of the folio. So the main idea of the folio was that they are a set of contiguous pages in both the physical address space as well as in the virtual address space. And this can be achieved this way, that when we are requesting for more space via a system call, what happens is that we are given a set of pages which comes from buddy allocation, and these set of pages are essentially one folio because they were allocated in one go, and they are contiguous in both the physical space and as well as in the virtual space, right? So that is how this adds up to the relevance of folios. So let me explain buddy allocation with a very simple example. It will be kind of clear. So let us say that the total memory size is 128 kilobytes, and I as a process need a 20 kilobyte chunk. So basically I need 5 pages. So what I can do, so here let's assume that all of it is free. So it would be unwise to kind of allocate, some part of it without some sort of a structure. So I first divide the chunk into two empty 64 KB structures, and one of the 64 KB ones, the left one, into two further chunks, 32 KB each. So in one of those 32 KBs, so I can further divide it into 16, but that will not cut because the amount of space that I need is more than 16 KBs, it is 20 KBs. So one of them over here, I allocate 20 KBs and I pretty much return the chunk. So of course you may want to argue that this space is wasted, and essentially I'm seeing some kind of intra buddy fragmentation. So I'll discuss what a buddy is, but this is a buddy chunk. So I'm having some fragmentation and some wastage. That part is correct. I won't blame you if you think that way, but the idea with this is that this is a simple approach where I'm taking a large chunk of memory, and it's a large contiguous chunk. I'm kind of dividing that into a binary space, and I'm essentially finding the biggest chunk or bucket, as you may want to call, that is a power of 2, and that is just about larger than the chunk that I wish to allocate. So the moment I have that, in that what I do is, let's say I want to allocate 20 kilobytes, I allocate 20 KB here and 12 KB is free. So basically this works in this power of 2 kind of fashion. And now let's say that I keep on allocating, then over time what could happen is that if another allocation for 64 KB comes, right? So in this case, By the way, what has happened is that if you actually see, I'm only considering the leaves. Of course, I could propagate this information to the top level, that this much is kind of allocated over here. So some information is propagated, but I'm not showing that in the figure. So in the figure, if we just consider the leaves, it is possible that at a later point of time an allocation request could come for 64 kb. So in this case, this entire 64 kb chunk could be taken, because as you can see, no other leaf is free that has that much of space. Now let us say we want to delete the 20 kb chunk. So the buddy system allows deletion also. But before I go forward, let's discuss where the name buddy comes from. So what I'm doing basically here is I'm creating two compound pages of 32 kb each, as you can see. So basically these two are buddies of each other. So if this is, let's say, compound page 1 and this is compound page 2, and of course their sizes are 32 kb each, they are buddies of each other. P is the buddy of P dash and P dash is the buddy of P. So the idea is that whenever we split a region, we create two buddies, and we can further split a buddy and then create two more buddies and so on and so forth. Buddy means a friend, right? A buddy means a very close friend, and it is an American term, right? So this is not that frequently used in the rest of the English speaking world, but that is the main idea of a buddy, that you create two blocks which are kind of friends of each other, right, counterparts of each other. And we'll see that this idea is quite useful in itself, of how both the buddies relate to each other. So we'll discuss that when we discuss their addressing. So now what happens is that if you delete this 20 kb chunk, then both the buddies, so 32 kb becomes free over here, this becomes totally free over here. So we can pretty much coalesce them and then kind of kill them, and then make this a leaf basically, which is what I have done. So I've made a 64 kb compound page a leaf, and its buddy is the 64 kb region again, which is full. So this, needless to say, the size of each buddy, which is a power of 2, has aided this process, and of course adjacent chunks, which are buddies of each other, which were 32 each, both became free. So we decided to merge both of them and have a single 64 kb chunk. So here again the idea is to try to minimize internal and external fragmentation, even though there is some fragmentation which is not to our liking. But again, that is an inherent part of the buddy scheme. But given this kind of binary approach of dividing by 2 and essentially trying to allocate that chunk which is just about larger, it's still a power of 2, but it's just about larger than what we need. That's basically the main idea. And the big advantage is that we can handle both small regions and large regions, in the sense small requests and large requests, in the sense that if let's say we want many 1 kb chunks or many 4 kb chunks, let's say 4 kb, that's the size of a page. So many 4 kb chunks, that can easily be done. If we want one large chunk, that also can be done. So we can clearly cater to all kinds of requests using this system. We will of course waste some memory, I'm not denying that, but that said and done, we'll be able to cater to a large number of requests which we wouldn't have catered to earlier. So the main idea now is to create a data structure to effectively manage the buddy list in the kernel. So it's a buddy list, I mean it's more like a buddy tree. So we'll see how to create such a data structure. So let us go back to the zone data structure. So in this case, what we had is that we had a structure that we had not discussed when we were discussing the zone data structure. So this becomes quite important right now. So we have an array of these struct free areas, and how many we have, max order number of elements, that's the maximum. So it's important to understand what is a struct free area, and why is it so important, and how is it tied with the entire buddy allocation system. So what happens is that a struct free area is basically a free list So sorry, it has a list, linked list called free list, where we have basically it's an array of linked lists. One array for unmovable pages, one for movable regions and reclaimable and so on. But as far as we are concerned, it is a single, if you are considered, if you are looking at regular pages, then we are interested in only one of these free lists. And of course, this also mentions, how much, what part of the memory that the zone maps is free. But as far as we are concerned, we are not really looking at different migrating types. We are only looking at the non-migrating type. And in that, it will be a single linked list. So a free area basically encapsulates a linked list. But let's understand what this array is about. So this array over here, right, basically is an array of max order entries. So the first will be, let's say, 0, 1, 2, and so on. So we will assign an ordering to a buddy system. So what we will say is that if we are looking at, let's say, a single byte, that will be an order 0. If, let's say, we are assuming that we are looking at the boundary of 2 bytes, then that is order 1, so on and so forth. So what we do is that order 0 is basically all the regions that we have free in our buddy tree. So if I consider my buddy tree, right, then pretty much, let's say, if log of this size, so this is like at order 6 and this is at order 7. So then basically the linked list for order 6 would have a record of all of these structures, and a linked list at order 7 would have a record of all of these structures. So the key idea is that we assign an order to each level of the tree, which is a function of the size of the bucket. So the size of the bucket is 128 bytes. So the order will be log 128 to the base 2. And of course, we maintain a list of all of these buddy pages. A page is a compound page which points to, some power of 2 bytes. So basically, we keep a linked list of all of them, right? Because we are interested in only one migratable type for our current discussion. Otherwise, the structure becomes slightly more complicated. So for every order, we have a linked list. And as I said, depending upon the body tree, you will have different orders and consequently different linked lists. So let's discuss this more with examples. So what you do is that whenever you want to allocate some page, right? So basically, or you want to allocate a region, you traverse this free area. So the free area is nothing but a set of linked lists, as you can see. You traverse them with an increasing order. So if this is the current order, and till it is less than max order, which is the maximum size of the maximum size of the order, we just keep on incrementing it. So the first thing that we do is that for the current zone, we go to the free area, and for whatever is the current order size, we get the free area struct from there. And then then we see whether we are able to get something. We are able to get a page which is a large compound page which encapsulates the region that we are interested in. If such a page can be gotten, so then we will call this function get page from free area. And if we don't find a page, then of course we continue and we increase the order. So let me explain what is happening. So what is basically happening is that, let us say, the current order. So when I start with order, this is basically the order of the page that is required. So let us say I need 20 kbs. Then I'll kind of up round it to 32, because 32 is basically what I need. Then I take 32 to the log 2, which is 5. Essentially, for to fit a 20 kb page, I'll look at 32 kb pages, 64 kb pages, so on and so forth, until I find one, right? And the moment I find one, then I will allocate it. So if I don't find one, then what I do is I increase the order and I kind of walk up the tree. And the moment I find one, instead of continuing, I'm going to come over here. Then I'm going to delete the page from the free list. So mind you, what we have over here is a list of free pages of that order size, right? Whatever is the order size. So I'm going to delete the page from there and I'm going to return the compound page. So essentially what I'm doing here is I'm traversing the list of free pages. Of course, technically I should traverse all of it, but I don't have to traverse the entire range. I just have to traverse from whatever is the order of the request to max order. Then what I do is that for each order, I basically access this structure over here. So this structure over here points me to a list of free pages of whose size is log of their size is equal to that order. And the moment I find one, I kind of come over here, I delete it and I use it. I delete the selected page and then I start using it. So then the idea is that if I want to kind of see that how do I use this. So what is the function that I was doing? So I was trying to get a page from a free area and do it. And the reverse would be that if I want to merge free pages, right? So in the previous case, there would be a need to split pages if it's a higher order, right? And then do that. So as I had shown, we were doing something quite similar over here, where we are splitting and doing that. So I'm not really showing the splitting code over here. But now if we go do the reverse, which is that let us say I want to free a page. In a sense, I have this page over here. PFN is the page frame number of that page. It is there in this zone and the order of this page is this. Now I want to free it in the sense I want to give it back to my buddy system such that my buddy system can can take control of it and possibly give it to another process who is interested in a similar size region. So the first thing that you do is that you find your buddy page, right? You find the page frame number of your buddy page. So what information do you need? Well, the information that you would need is the current page, the current page's page frame number and the order. So here is the interesting equation that we have, which is very easy. The page frame number of the buddy, right, is the current page frame number exclusive ORed with 1 to the power order. Okay, so basically this could be reasonably hard to understand. So let me just explain that with some free space in some free area in a free space. How we came across this this equation. So I'm searching for some little bit of free space over here. So essentially is buddy PFN is equal to my PFN exclusive ORed with one left shifted order times, right? Let us now consider these two buddy pages and let us say the starting address of this is 0. Then the starting address of this is 64 KB. So let's factor out 1 KB and then let's see, let's just focus on 64. So 64 in binary, right, is 8 into 8. So it has 6 zeros before it. So that is exactly what 64 is in binary, right? It kind of looks like 1 million, but it has 6 zeros before it. Well, why? Because 8 has 3 zeros and then another 8 has 3 zeros. So this 3 plus 3, 6, right? So that's the way it is. So in this case, as you can see, we have two pages. So the address of the first page is 0, 0, 0, 0, and the address of the second page has a 1 in the MSP position. So basically, if let us say the first one is PFN, the second one, which is buddy PFN, this is nothing but PFN exclusive ORed with 1 left shifted 6 times. So 1 left shifted 6 times would be what? 1, if it is over here, left shifted once will come here twice, 3 times, 4 times, 5 times, 6 times. So 1 left shifted 6 times is nothing but this value over here. And the moment we exclusive OR that, right, with this, we actually the moment PFN exclusive or one left shifted 6 times, it is nothing but this address, and this address is nothing but the starting address of the body page frame number. So the way that you relate the body page frame number with the page frame number is one left shifted order times, right? Where order is, as we have discussed, log 64 to the base 2, which is 6. Now let me just clear off the clutter in the slide. So what we get to see over here is basically that the overall order is what determines what are the relative addresses, and this is independent of the body size. It could be 64, 128, 256 kb, whatnot. But this equation would hold, which is basically that body PFN. So essentially what we do is that we can take the address of this and we can zero out the one, and we will come back to the address of this. And basically it is the same thing that we zero exclusive odd with 1 is over here, and one exclusive odd with 1 is 0, which takes us back over here. So given that this equation holds, what we can do here is that using this equation, we can find the page frame number of the body, and we can find the page frame number of the page. So that anyway we know. So this is basically an input, but for the body we will find it from here, right? So then we will find the body over here. So now what we can do is that if we are merging free pages, then we can delete the body from the free list, right? Because the body will have the same order as the original page. And if the body is known to be free, so that's the reason we are merging in the first place, then what we can do is we can delete body from the appropriate free list, which is the free list of zone, the ordereth free list of zone, right? So that we can delete the body from there. And then to get the PFN of the parent, here again there is an interesting bit of binary algebra. This is nothing but body PFN and PFN, right? And the reason for this is that if you actually see for both the body and the original PFN, the first MSB bits are the same, and it's just at the one left shifted ordereth position or the ordereth position, right? If I count, I'll count an order number of zeros over here, right? So the number of zeros is ordered, and then if I look at the position, then for 1 it will be 0, for 1 it will be 1. So if I take the combined PFN, which is nothing but the PFN of the parent, then all that I need to do is I need to AND them out. And if I AND them out, then what I will get is that 0 ANDed with 1 will become 0. So of course, you could argue that I could choose one of them. I could choose this one to be the parent, right? Because anyway, we need the starting address of the parent, which will be the starting address of one of the bodies. But again, it does not happen that way because we don't know which one is the original page and which one is the body. So it's always the best to take both and kind of AND them. So once we have done that, we have found the combined page frame number. So this is the page frame number of the parent. And then what we can do is that we can find the offset of the parent's PFN to the current PFN. And we can add that to page. So this will basically give you the page of the parent. That's all. And PFN equal to combined PFN means that you are setting the state to the parent's page, right? And then you increment the order. So of course, I've deleted some lines. So basically, I never show all the lines in the code. But the main idea is that you merge a node or a bucket with its body if both of them are free, right? Otherwise, you don't merge. And in this case, you would keep on merging, and as you can see, a deletion is also happening. You will keep on merging and you would keep on deleting until you reach the very top or until you reach a position in which the body has data, right? So once that has been done and we have exited the while loop, so what we do is that whatever is the current value of the order, we set the order of the page to that, and we add the page, right, which we created by combining, right? So this is the last stage, and the reason we stopped over here is basically either it's the root or because its body is not free. So once we stop over here, we add it to the free list of the specific zone corresponding to that order. So the main thing that we are doing, if you kind of walk back over here, is that if we delete this 20 KB chunk over here, we will combine this and this, and then we will of course obliterate both of them. We will go to the 64 KB part, but we will see that its body is not empty, it is full, right? So, or let's say it's non-empty. So that's the reason our combination process will stop over there. So what we have seen is we have seen both the ideas. We have seen how a page is allocated. So of course, I didn't show all of it to keep matters simple, but at least we saw some part of it, with the relevant part of it, right, in page alloc.c. And in this case, we saw the part where we merge the free pages, and we kind of keep merging, and we keep walking up the tree until we stop at one point. What is that point? Either that point is the root, or it is the point where its body is not free. So now that we have discussed the buddy system, which is a generic memory allocator, right? So it does not differentiate between one kind of an object and another kind of an object. Let us now look at a specific region of the physical memory that is explicitly tailored for storing objects of a specific type, right? So it has a very, it has a rigid and fixed structure. So in this case, we need to make several observations. The first observation is that there is no reason to allocate and deallocate an object, a frequently used object like a task struct or an struct, right? Or one of those file structures that we shall see. The reason being that, once we are done with them, we could of course reset some fields, but we need not deallocate them and remove them from memory because we'll be using them frequently. So create a dedicated object storage area for, of course, known objects whose size, etc. is all known. And furthermore, use this as kind of a pool of objects or a cache of pre-allocated objects, where if you want to get an object, you don't have to like go and find a new memory area and initialize one. That all of that takes a lot of time. But just maintain a pool of objects or a cache of objects which are all pre-initialized. So pre-initialized would basically mean that the space has been allocated to them. They already exist in memory. All of their read-only fields have been populated, and they are all they are fit to be used. So in this case, all that you need to do is you need to get one, do some bookkeeping, and use the object. And once you are done, return it back to the pool. So we will look at many different terms over here: a slab, a cache, a chunk, and so on. So, but the basic idea of the slab allocator is for dedicated object storage where the objects are very frequently used. It's a dedicated object cache. So the kernel, as we have discussed, has three object allocators. One of them is a slob allocator. So slob allocator uses the old first fit method where you kind of scan and find the first available hole. Where you can fit in an object, right? So we have seen that earlier, and but as I said, you can have these holes between memory regions which are either very small or very large. So these voids between these places, right? So they are called filled regions and empty regions or holes. And the issue is that this is not very efficient. So as of kernel 6.2, the rumor is that the slob allocator will be kind of unused, deprecated. What will be used is a slab allocator, which is very popular, and the new slab allocator, which is way simpler, and its scalability and performance are definitely much better, right, as compared to slob. So we'll not discuss slob at all. We'll discuss slab and slub. Okay, so the slab allocator looks like this. Don't get intimidated by this diagram. We will go step by step. So the key idea is that for every object type, so you won't do it for all object types, but some of the objects types that are close and dear to you, like a task struct and, as I said, struct, right? And then in a file operation structures and some device structures. So a few of them, the ones that you frequently use. The idea is to create a KMM cache. A KMM cache is nothing but a dedicated memory region for object storage. So in this case, what it would have is that it would have a per CPU array cache, where an array cache is nothing but an array of entries, and these entries are recently freed objects. So in a sense, they are warm. Warm means that their state is there in the CPU's caches, the hardware caches, not the software ones like KMM cache. But the CPU has them in the hardware caches, so they can be used. And they were recently freed on the current CPU, so they are definitely, good and fast data, right, which is ready for use. So the array cache is a per CPU data structure which makes things efficient, right? So that's the first plus point. The other thing is that since we are not allocating and deallocating objects, but we are essentially reusing them, reusing objects is slightly problematic because they still would have some state. So that's the reason it is necessary to provide a function which would get rid of all the state that you don't need, or all the state that the previous function was using, and reinitialize the state, essentially construct the object, right? So of course, the object constructors are called the very first time when we are allocating them, but because the point is that an object has to be constructed, its layout in the memory has to be constructed, we'll have to fill it in with all the read-only parameters. So this function is primarily for that purpose, but it's not uncommon to once in a while use this to reset the state of an object if there is no easy way to do so. And then what we have is we have a bunch of, for every NUMA node in the system, we have a KMM cache node. So a KMM cache node is basically nothing but a localized KMM cache for every NUMA node in the system. So let us see what each of one of them contains. So each one of them basically contains three lists. And these three lists are lists of slabs, where a slab is a contiguous memory region that contains multiple objects, right? So a slab is nothing but a memory region, right, which is typically a multiple of pages. So let us say that the size of an object is a quarter of a page, basically 1 KB. A slab could comprise, let's say, 16 KB of memory. So that would be 4 contiguous pages, right, 16 KB of memory. And given the fact that, let's say, an object is a quarter KB, so then yes, a quarter KB, 16 divided by a quarter is essentially 64 objects. So 64 objects can be stored inside a slab, and each such memory region to store an object is known as a chunk, right? So the key idea is that a slab is a contiguous memory region that comprises not one but multiple physical pages. So that is a slab. And what we do is that slabs can have different states, in the sense, if the entire slab is full, in a sense, not a single free chunk is available to store an object, it's a full slab. So what we'll do is we'll have all full slabs in a linked list whose head is called full. If, let's say, slab is partially full, in the sense there is still some space to store objects, we will store such slabs in the array partial. And finally, if, let's say, nothing is stored in the slab, then we'll say it is free, right? It's totally free or empty. So what we will do is that for every NUMA node, we'll have a sequence of such slabs which are either full, partial, or free. Free meaning empty in this case. And a slab is a contiguous memory region which is typically several pages, an integral number of pages. And this entire memory region is treated as one unit. Within this memory region, we kind of break it down into chunks where each chunk can store an object. So looking at a slab, so slab of course has a back pointer to the slab cache, which is the KMM cache. So there's no point considering this. The SMEM pointer is a pointer to the memory region that actually contains all the data corresponding to the slab. So here we will have all the objects, and we will have this structure called the free list, which is nothing but a bitmap of object indexes, right? So it's called indexes. So in India, in general, we use the term indices as a plural of index. But by far in American English, what is used is indexes. So we'll use that. So again, it's a matter of convention. It's important to understand that we'll use this term. And the free list basically is an array that comprises the indexes of all the free objects. So there are many ways that this could be implemented. You can implement it as a bitmap, as an MDBOS tree, or just as a regular linked list. So the regular linked list is clearly the simplest if you just want to keep indexes of free entries, right? So that's always free chunks basically, right? A chunk entry, the same thing as far as the literature with regards to slabs is concerned. But again, the key idea is that these free positions over here, they are all maintained within this linked list called free list. So what we see is that the slab idea or the allocation of a slab is reasonably simple. What we do is that the moment we are asked to allocate an object, right? So we locate the KMM cache that corresponds to that object. Then we go down to our NUMA node. There we only focus on partial slabs, and then we get a partial slab, we go to the free list of the partial slab, pick out an index of a free entry, and we kind of take that entry. Clearly, when there are no partial slabs, in the sense that the linked list partial points to an empty linked list, then we use the free linked list to get a slab which is absolutely unallocated, and we start allocating there. And then of course this slab moves from free to partial. So as you can see here, the notion of this hot pages is there, basically hot objects. So the idea is that if, let's say, an object was being used and it has been recently deallocated, then its state would be there in the CPU's hardware caches. So we can store it inside this array here for quick access. In case we don't find it, then of course we'll have to walk down the list of slabs. First the list of partial slabs, then the list of free slabs, and find a slab, right, for use, right? And so basically there also we'll have to traverse the free list, find a position, and then take that object. The slab allocator would be much simpler, right? But before we go to the slab allocator, a couple of quick explanation points are important, even though we have discussed almost all of it, but I want to ensure that we are not missing anything. So of course the slab is a dedicated region of physical memory and also the kernel's virtual memory where we store slabs. Each slab is basically a contiguous region, and then again it can store finite size, fixed size objects. And a free list essentially says that whether an object storage location, a chunk, is free or not. And the KMM cache is essentially the directory of slabs. So given a certain object or an object type, and let's say it's a PID struct or something, and that is managed by a KMM cache, then from the object type we go to the KMM cache, and there we start searching for free objects. I mean pre-initialized objects which will be given to you. In case you are not happy with that, then of course the constructor can be called and the entire initialization can be repeated, even though it's a rare case. Then we have discussed this full, free, partial, NUMA nodes per CPU caches and so on. So the idea here is we minimize the number of KMM cache structures. We don't want to have many of those because of the complexity. And in general, the slab scheme is complex. So I did explain it to you, but if you look at the code, you'll find that the code is reasonably complex, and it is not something that we would like to, at least replicate for every single type of object. That's where you come to slab. So slab is, in comparison, much simpler. Even though we have the same high level structure, we have a KMM cache. So the KMM cache here, it again has a per CPU cache. So the per CPU cache basically has a single slab under its control. That's all. So the per CPU cache just is a single slab where you can have, of course, multiple objects, and there is a free list which is an array of these pointers. It's a void star star, means basically means it's an array of pointers, And the array of pointers basically points to, or let's say lists all of the locations within the slab which are free in the sense as objects are not being used. So this is sufficient for most cases, in the sense the idea always is to use this slab as the per CPU slab for quick object allocation and deallocation. So when something is deallocated, it can be returned to the, well, if it's from the per CPU slab, which means this slab, it will of course have to be returned here. But if it's from some other slab, it has to be returned over there. So clearly we are not entertaining the possibility of taking an object from slab A and returning it to slab B, because that is not possible, right? Because the addresses are hardwired. So then what we have is that we have, this same usual suspects. We had uint object size in the earlier case also, even though it didn't appear in the diagram. Then of course an object constructor function is needed. And then a KMM cache node, one per NUMA node. So this was also there. So no surprises here, but a massive surprise over here. So we don't have the full list and we don't have the free or empty list, right? The free or empty list, both of them are not there. So this basically means that once a slab becomes full, we forget about it. We simply forget about it in the sense that we just don't maintain any state. And once an object is deallocated, if we find that the region in which it was deallocated corresponds to a region in the slab area, we'll figure out that yes, it got deallocated from a slab, and we can figure out the slab, starting from the address that was deallocated. We can always walk back and figure out the starting address, because you're assuming that the starting addresses of slabs have a certain alignment. Let's say if a slab is 64 kbs, we are assuming that the starting address would be a multiple of 64 kbs. So in this case, of course, we'll add it back to the set of partial slabs. We are also not maintaining the state of fully empty slabs. The reason being that we are using the regular Linux's regular buddy system, the memory allocator, right, to kind of keep track of it. And since it is already doing a good job, we don't have to do a better job. So we will basically take the entire slab region, and whatever slabs we are using, of course, they will be marked kind of used. But whatever we are not using, which will correspond to these free or empty slabs, we will let the existing memory manager, which is nothing but the buddy system manager. So manager is a combination of an allocator and a deallocator. Let the buddy system take care of these. And when I need something, I will ask the buddy system to basically give me a slab, right? A slab worth of contiguous memory between a start and end, which is essentially the slab region. For the slab itself, it will have a back pointer to the KMM cache. Again, no surprises over there, right? It will, of course, so given a slab, from the starting address of the slab, you're assuming that in this we don't have a separate SMEM like thing which pointed to a memory region. You're assuming that whatever is the memory region of the slab, the entire storage area also starts from there, with the first few bytes taken up by this metadata, right? So that assumption is there. But that does make everything simpler, because we don't have to have a separate pointer. Of course, what we need to have is, we need to have some statistics, in the sense in how many total objects are there, how many are in use, and how many are frozen, in the sense that they cannot be touched, they can't be removed. And then of course we need a free list. So we need a free list to point to all the objects within the slab which are currently not used or unallocated, right? So the free list is always needed. It's needed over here. And of course, a free list is always a part of a slab, right? So that is always needed. So the key point over here, if we look at it, is that the basic idea is by and large the same. If I just take you back to the slab allocator, that also looked reasonably simple. So the basic idea is by and large the same, even though a solid effort has been made to kind of compress all the data and also reduce the amount of data. So what we are doing over here is that it's an interesting hack in the slab allocator. So there is no term slab, by the way. The name of the allocator is slab, but there is no term called slab. So we are kind of fusing the place where all the objects are stored along with the metadata in the slab. So then We don't have to store any separate pointer. Furthermore, per CPU, instead of an array, we are storing a slab. Again, that homogenizes things. And homogeneity always means elegance, simplicity, and good performance. And finally, instead of full and free, so basically, the other two linked lists, the realization is very clear that if the address region for a slab is known, the moment a full slab gets deallocated, at least an object gets deallocated within it, it will move to partial, and the moment that something gets allocated within free, it will also move to partial, right? So basically, it is known that something which is free, that should be managed by the memory system. It's much more the buddy allocation system. That it is much more efficient that way. When we need something, we can always get it from the buddy allocation system. So this is simpler. This is by far much simpler and efficient. But again, in some cases, we need the flexibility of the slab allocated as opposed to slab. So clearly here, simplicity is a big plus. The KMM cache is still there. The free list is still there. And instead of a per CPU entry of objects, we have a per CPU slab, which again, this was done for elegance and homogeneity, which is always a good thing. And we get rid of full and free, as we have discussed. We just finished discussing. And the partial slab list is the only thing that is the only list that is important. Where from the full and free, you can happily move to partial depending upon the action that is performed. So clearly what we have seen here, right, is that we have two kinds of allocators which are very different characters. So the buddy allocator basically kind of superimposes a tree. It's not a balanced tree, it's an unbalanced tree, it's a highly unbalanced tree, but it superimposes a tree nonetheless on what is a flat memory system. Then it defines these regions and basically a buddy associated with the region, where essentially if you flip a bit, you go to the starting address of the buddy. So we have seen that. And the idea here is that you keep on splitting a region by 2 until you find a region which is a power of 2 bytes, which is just about larger than the object. And similarly, we can combine them and this tree can shrink also if, let's say, if let's say small objects are not being allocated via this method. This method kind of feeds into the fact that a dedicated object storage is required. So first we look at slabs where we just take a region, we just demarcate a virtual memory and physical memory region, say that this part is mine and I'll use it to store slabs. That's fine. So here we'll have a cache node which is optimized for frequent access, in the sense not everybody would want to traverse the list of slabs. But again, the flexibility is provided that if you want, you can, and you can pick out objects from slabs, right? So that's a big plus. And the slab allocator was becoming complex, so we went to the slab allocator, which is quite practical and quite fast. So the slab allocator, even though is not extremely popular as of 2023, its popularity is increasing. So there may be a possibility that, like slab also might get deprecated in the future, even though it is quite hard to say. It's quite hard to say that now, given the sheer popularity of slab, whether it will be deprecated or not. But one thing that is clear is that slab is coming out with some good ideas with regards to simplicity and elegance. And these ideas are bound to be appreciated. So this finishes the full lecture on memory systems.